All right, so this video covers the second half of Module 5. In Module 5, the big concept is that of the mole concept. But before we jump right into the mole concept, let's review a couple of things about the chemical formula, molecular formulas, and the atoms that are in them, and then we will talk about using atomic mass to calculate the mass of the molecule or the mass of the compound. The good news is that if you want to know how many atoms of each element there are in the formula, that's pretty easy. You can just read it right off the formula. So for example here, sodium phosphate, sodium Na, there are 3 sodium atoms, 1 phosphorus atom, and 4 oxygen atoms in that sodium phosphate molecule. The next one's a little more complicated. This is calcium acetate. Calcium acetate has got 2 acetate ions. That's inside these brackets there. That's an acetate ion, C2H3O2. It's got 2 of those. That's what this subscript out here is for every 1 calcium atom. And so if you want to know how many atoms of calcium are in this molecule, well, there's 1 calcium. There are 4 carbons because there are 2 times 2. There are 6 hydrogens, 3 times 2, and there are 4 oxygens. And you can calculate that of aluminum iodate. So there we have a real quick review of the chemical formula and the number of atoms. That's going to be essential if we are now going to use the number of atoms to calculate the compound mass. So here we're going to be looking at the same set of molecules. And all we're going to now do is jump from the number of sodiums to the atomic mass of sodium. So sodium has an atomic mass of 23. Up here it says 22.990, but it's pretty close to 3. So we're going to round that up to 23. And there are 3 of them. So if I want to know what the atomic mass of my compound mass is, I'm going to add up however many sodiums I got, plus however many phosphorus, plus however many oxygens. And so that's 3 times 23, plus there's only 1 phosphorus, so I just put that 31. Phosphorus is right there. There are 4 of the oxygen. Oxygen that's 16, 15.999, simplified as significant figures, and I come up with 164.0 atomic mass units. So before we can ever work with our mole concept, one of the first things we need to be able to do is nail down the atomic mass of a compound. So I'm going to let you work through calcium acetate, aluminum iodate, ammonium iodate, and lead-4 sulfite, and calculate their compound mass. Go ahead and pause the video and do that. All right, now let me show you some answers. There we have the molecular mass of those molecules, the compound mass. And you'll get lots of practice adding up compound mass from atomic mass as we move through the class. So it's worth your time. All right, next thing we're going to look at is the mole concept. This is a very, very useful concept that enables us to actually do a lot of the chemistry that we want to do. So here's why the mole concept is so important. I asked the question, can we weigh out a few number of atoms? Well, the answer is no. Atoms are inconceivably small in size and small in mass. But if we have lots and lots and lots of atoms, eventually we get to a mass that we can weigh. The mole enables us to do just that. And the mole is a very, very large number. It's recently, I think in 2019, I think it's actually been defined now exactly as this number here, 6.0221407 times 10 to the 23. So we got lots of significant figures if we ever need them. For our class, for the most time, we're only going to use 3 significant figures, and we're going to use the number 6.02 times 10 to the 23rd. So that's the one you're going to have to remember. That is called a mole. That's a number of things. It's also called Avogadro's number. There was a French chemist who actually came up with this number, but Avogadro did a bunch of work with gases, and we'll later talk about that with the Gay-Lussac's law. But he was able to determine that there was some number, he didn't know what it was, but it represented the mass of a certain volume of a gas, and gases, masses, and volumes go together. So actually, volumes and moles go together. I shouldn't say masses, but the number is given the name of Avogadro's number, and we also refer to it more often as just the mole. So I'd like to give you an example of just how big of a number this is. Let's say there was a mole of you. Let's say that you took your mass in kilograms and multiplied that by a mole. What would the number of kilograms be as a result of that? And the way you can do that is there are 2.2 pounds for every kilogram. So if you know your weight in pounds, you can take that, divide it by 2.2, and that'll give you kilograms, and then just take that mass and multiply that by Avogadro's number, the mole. So when I take my weight in pounds, that's roughly 180 pounds, I divide that by 2.2, and multiply that by 6.02 times 10 to the 23rd, I come up with a number of 4.93 times 10 to the 25 kilograms. So I'm going to look and see what's closest to 10 to the 25 kilograms. Look at that. So it's 4.93 times 10 to the 25. It's really pretty close to Uranus. It's more than Earth, quite a bit more than the moon. I'm nowhere near the mass of the sun. But if you take a mole of me in kilograms, I'm about the same mass as the heavenly body we call Uranus. Okay, so the next thing that we want to get used to conceiving, thinking about, and hearing in our ear is the term molar mass. Sometimes that's just abbreviated MM, molar mass. That is the mass in grams of 1 mole of a substance. Now, I know just a minute ago I had you calculate the mass of your mass in kilograms and then compare it to the planetary bodies. But molar mass is always going to be calculated in grams, not kilograms. And so you can read off the periodic chart. If you know the atomic mass units, you can say something about a mole of those atoms. So, for example, we could talk about the mass of one atom of carbon-12. Carbon-12 is one specific isotope of carbon, all right? And carbon-12 has exactly 6 protons and 6 neutrons, and they have a mass of 1 AMU each, and so we end up with an atomic mass of that particular isotope of carbon of 12.0. Well, if I had a mole of those guys, I would have a mass of 12.0 grams. Or another way to say that, if I have 12.0 grams of the isotope carbon-12, I would have 1 mole of those carbon atoms. So molar mass has the same number as the atomic mass, but it's just different units. From that, you could calculate the mass of one atomic mass unit. So let's just say that we had one isotope of hydrogen that just has 1 proton. And we had a mole of those. I know that a mole of those has 6.02 times 10 to the 23rd units. So if I take that 1, divide it by Avogadro's number, I come up with an atomic mass of 1.66 times 10 to the negative 24 grams. So we've calculated the mass of one atomic mass unit in grams. The good news is we're never going to ever have to work with that gobbledygook number. We're going to be able to work with this. We'll call it 1 atomic mass unit, or we may call it a mole, but I'm never going to have to be working with that number. So that's good news. All right, so back to the big picture. We've now introduced the mole concept. We now had to calculate atomic mass and compound mass. Our next task is this. We need to figure out how to go from grams of a substance to moles of a substance. So for example, if I were to give you a sample of iron, let me show you a sample of iron here. This is a chunk of iron that we synthesized last year. Later on in the year, you'll actually do this same experiment. But what we did was we took iron oxide and we drove off all the oxygen from that iron oxide molecule, and we ended up with just a solid chunk of iron. Iron oxide is Fe2O3, and we used a tremendous amount of heat in order to drive off those oxygens, and we just did what we would call a decomposition reaction, like you studied earlier in the module. So we're going to go to iron plus oxygen, and we know that we got to balance that equation out, and so I'm going to need 6 oxygens on that side, 6 on that side, and then 4 iron atoms on this side. So that's basically the reaction that we did, and lo and behold, look at what we produced. So let's say I wanted to know how many moles of oxygen that I have right here. Or excuse me, how many moles of iron that I have in my hand there. This is the iron that I produced, and I want to know how many moles I have of that. In order to figure that out, all I have to do is determine the mass of this, and then I look at the atomic mass units of iron, and I can then calculate the moles of it. So let's do that. We're going to go to the scale and determine the mass of that. So when I weighed that on the scale, I came up with a mass of 50.19 grams of iron. Knowing the mass of it, and also knowing the number of grams in 1 mole, and we read that right off the periodic chart, I can calculate the number of moles that I have right here. Let's go through that. So when I take the mass of my sample and I divide that by the number of grams in 1 mole, I come up with 0.899462237. Obviously, I can't keep all of those digits there because I only have 4 significant figures here. Actually, I only have 3 significant figures there. I guess what I could do is rewrite my iron, and let's see if I can get 4 significant figures with that. So if I go to my periodic chart, iron looks like I have 55.933 that I can use as my atomic mass. A little different from that in Wiley's book. And so when I get rid of the 55.8 and I use the 55.933 from the other periodic chart, I take 50.9 or 50.19 divided by 55.933, I get 0.89732 ... Well, I have 4 significance here, figures there, I have 5 there, so I can keep 4, so I can keep 1, 2, 3, 4, so I can end up with a molar the number of moles here of 0.8973 moles of iron. So all I did was I started with, I was given a sample, and I said, okay, how many moles are there right there? Well, I took that sample, put it on the scale, got the mass of it, determined the number of grams in 1 mole of it, and then from there I could determine the number of moles that I have. And that's basically what we're going to do an awful lot of in chemistry. So what I've done is I've converted from grams of something to moles of it. Very helpful. We also want to be able to work the other way around. If I know the number of moles of something, I ought to be able to then calculate the grams. So if I were to say that I had 0.8973 moles of iron, I should be able to rewrite my equation, recalculate it, so that I end up with 50.19 grams. So I have a work project for you to work through. I'm going to give you an example of a mass of a compound or an element. Here's copper, single element. I say I have 156 grams of it. You calculate or just read right off the chart, in this case, the atomic mass of copper, which is 63.55 atomic mass units, and then you calculate the number of grams then you calculate the number of moles. Sorry about that. So for in this case, I'd take 156 grams, divide that by 63.55, and that's going to give me the number of moles. So I'm going to go ahead and have you work through the rest of these, and then I'll show you a screenshot of the answers. All right, and here's a quick screenshot of the answers. I gave you the stuff in black, and the answers are the stuff in red. There we go. All right, let's move on. Let's talk about the meaning of chemical equations, and then that'll give us something to kind of give you a sense of the direction of where we're going in next module in particular. So let's look at this equation right up here. CH4, that's a gas called methane, and that G doesn't mean grams, that G means gas. And O2, you're familiar with that, that's oxygen. You should be familiar with carbon dioxide, that's a gas as well. And then here's water, which is in the gas phase. What the chemical equation says is that if I have methane, and I burn it in the presence of oxygen, and you now know that is a complete combustion reaction because we have carbon dioxide and water. That should be pretty familiar to you after this module. That I can say something about the number of molecules that are reacting here, or I could say something about the number of moles that are reacting. So for example, I could say that if I have one molecule of methane, it reacts with two molecules of oxygen to give me one molecule of carbon dioxide and two molecules of water. Or instead of talking about individual molecules, I could say that if I have 1 mole of methane reacting with 2 moles of oxygen, that's going to give me 1 mole of carbon dioxide and 2 moles of water. And that's what we're trying to show here. This is kind of a dated graphic, because in this graphic it gives you the number of Avogadro's number of a mole a little bit different. This says it's 6.023 times 10 to the 23rd. And we are now defining it as 6.022140076 times 10 to the 23rd. So don't refer to this graphic for the mole number, but it's basically the same thing. But that's what the meaning of the chemical equation is. And where we're going with all this is, if I start off by saying, look, if I have 25 grams of methane, and I want to know how much water is produced given this equation. And you could probably figure that out at this point. We're going to do a lot with that next module, but we'll just kind of talk through it right now. If I have 25 grams of methane, I could figure out how many moles of methane that is. And if I know how many moles of methane that are in 25 grams, I have a relationship between moles of methane and moles of water. There's 2 moles of water produced for every mole of methane. So all I have to do is figure out how many moles are 25 grams of methane, and then go from there to calculate how many grams of water would be produced. So now we have a very powerful tool here. So if we start with 25 grams of methane, we can figure out the molar mass of methane just right off the periodic chart. That's going to be 16 grams of methane per 1 mole. If I take 25 and divide that by 16, just stop right there, that will give me the number of moles of methane in 25 grams. So I could write that down. That would give me 1.56 moles of methane. But let's just go ahead and keep thinking about this. I know that there's a molar ratio. In my formula, for every 1 mole of methane, there are 2 moles of water that are produced. So I could take that 25 grams, divide it by the 16, we know what that is, that's 1.56, and then multiply that by 2, and that would give me the number of moles of water produced. But let's take that one step more, because what we really want to know is how many grams of water are produced from not just the moles. Well, I know that 1 mole of water has 18.02 grams, and there are 2 moles of water. So I could finish that out, and I could say, oh, okay, well, I calculate that at 16.95 grams, but I only have 3 significant figures, so I'm going to round that to 17.0 grams of water. But you can see we did something very, very powerful here. We used the molar relationship between methane and oxygen and water, and we figured out how many grams of water would be produced if we started off with 25 grams of methane. That's good chemistry calculating right there. And we're going to be doing an awful lot of that in modules to follow. But let's do some far more simpler practice problems. This is stuff that we'll work with next module. I just want to show it to you where we're going. But let's do some practice problems that are not nearly that involved. All right, these are the problems I want you to work on. I want you to convert, if you have 0.0027 moles of water, I want you to tell me how many molecules of water you have. Keep in mind that for every 1 mole, there are 6.02 times 10 to the 23rd molecules. So you're just going to take 0.00277 and multiply it by 1 mole, or 6.02 times 10 to the 23rd, and that will give you how many molecules. Let's look at this next one. How many moles of lead sulfate are there in 3.65 times 10 to the 25 molecules of that? Oh, well, let's think through it. If I say that there are 6.02 times 10 to the 23 molecules in every mole, I can just say, okay, 3.65 times 10 to the 25, divide that by the number of molecules in 1 mole, and that'll tell me how many moles that I have there. So I think you can follow the reasoning through there. Go ahead and work your way through all of these problems here, and I will give you a screenshot of the answers. So shut the video off and do some work. And here's a screenshot of some answers to those problems. I'll let you compare your answers with the answers that I got. All right, that is it for the second half of this module. The lab that we're going to be doing next week is we're going to put all of these tools together. We're going to put the fact that now we know how many molecules are in a mole, and that there's a way that we can weigh things out to determine how many moles we have. We're going to put all that together with some simple geometry, and we're going to actually measure the approximate width of a molecule. Sounds very ambitious, but it's fascinating to do. We're going to use some soap, some water, some pepper, and I'll give you another video where we talk through just how to go about doing that. But anyway, that's where we're headed for the lab.